The last thing we're going to look at in this section is theorem 5.15, which is the integration of even and odd functions on symmetric intervals. Let f be integrable on the closed interval negative a to a. This is very important, that the interval we're looking at has to be a symmetric one. So if you're on the x-axis, whatever positive distance we're going to the right, we're going the same distance to the left. So we're looking at an interval specifically of this type. If f is an even function, then the definite integral from negative a to a of f of x dx is equal to twice the definite integral from 0 to a of f of x dx. To kind of explain why that relationship holds, let's suppose we have a function that is even. One of the things you might remember from a college algebra class is that if a function is even, then it is symmetric with respect to the y-axis. So on any interval of the form negative a to a, essentially what's happening is any area you would have from negative a to 0 would be the same amount of area you would have from 0 to positive a. So instead of finding all of the area from negative a to a, you can simply just find the area from 0 to a, and then the total answer will just be double that. This is usually pretty time-saving, simply because using the number 0 in a calculation tends to simplify things as opposed to having to use any other real number. On the other hand, if f is an odd function, then the definite integral from negative a to a of f of x dx is going to be equal to 0. Okay, if you want to try to get some intuition as to why that's true, let's take a look at what would happen if we had an odd function. Something kind of like, let's say, like the graph of x cubed. If we have a symmetric interval from negative a to a, essentially what's happening is the amount of area you would have, let's say, in this case, below on one side, would be the exact same kind of amount of positive area you would have above on the other side between 0 to a and negative a to 0. Those would kind of cancel each other out, and that's why the overall result ends up being equal to 0. If you need a refresher on the conditions of what it means for a function to be even or for a function to be odd, f is an even function when f of negative x is equal to f of positive x for all x in the domain, and f is an odd function if f of negative x is equal to the negative of f of x for all x in the domain of f. Which brings us to example 10, integration of an odd function. If we want to evaluate the definite integral from negative pi over 2 to pi over 2 of sine cubed x cosine x plus sine x cosine x dx, this is one that we could certainly do by splitting it apart and doing two pieces and doing a u substitution. However, the thing that would make you want to double check and pause for a moment and look at theorem 5.15, is the fact that this integration is on a symmetric interval. And anytime you have integration on a symmetric interval, you should check to see whether or not the integrand is an even and odd function. So let me just call this function on the inside, let me call this little f. Let's let little f be the sine cubed of x cosine of x plus the sine x cosine of x. We can check this for even and oddness, but you might recall from just a basic trig class, cosine is an even function, sine is an odd function, and if you compose an odd function with an odd function, the cubic function is odd, that result would be odd. So what we have here is something that's going to be an odd function times an even function, and that result will end up actually being an odd function. Here, we have an odd function times an even. An odd function times an even function remains an odd function, and the sum of two odd functions is yet another odd function. So this function we have all together is indeed going to be an odd function. Let's just go ahead and verify that, though. If I were to substitute in negative x for x, this would produce the sine of negative x to the third cosine of negative x plus sine negative x cosine negative x. Again, using the even and odd identities for the sine function, this is going to be negative sine x cubed, because sine's odd. Cosine is even, so this is the cosine of positive x. Sine is odd, so this is the negative sine of x. Cosine is even, so that's equal to the cosine of x. And then here, if I have negative sine of x cubed, that's negative sine cubed x cosine x minus sine x cosine x. And if I factor a negative out of this entire expression, what we see is that this is equal to the negative of f of x. So we've shown that f of negative x is equal to the negative f of x, and that proves that f is odd. Therefore, using the previous theorem, if we're integrating an odd function over a symmetric interval, which we are, this result would be equal to 0.